Ignition sequence start. 6, 5, 4, 3, 2, 1, 0. All engine running. Liftoff. We have a liftoff.
Welcome to the Xterra Podcast. I'm Tom Patton. People of a certain age in our audience will remember the days when via satellite was an indication of the highest level of technology when it came to communications. Now, chances are, if you're communicating somewhere, there's a satellite involved in the process. There are major advances being made into satellite communications, and one of the companies at the forefront of those developments is Cesium Astro, which recently unveiled its Element Integrated Phased Array satellite. My guest on this edition of the Xterra Podcast is Shey Sabripour, the founder of Cesium Astro. Shey, welcome to the Xterra Podcast.
It's a pleasure to be with you, Tom. Thank you for having me.
Let's start out by talking just about your background and how you got into the space industry.
I'm an electrical engineer. After college, I joined a company called Lockheed Martin Space Systems Company, its predecessor companies, which started out near Princeton, New Jersey, in a town called East Windsor, New Jersey. It was called RCA Astro Electronics, became GE Aerospace, became Martin Marietta, and ultimately joined Martin Marietta and Lockheed joined and became Lockheed Martin. But I worked at Lockheed Martin for 24 years. As a design engineer, a manager, program manager, ultimately as a director of spacecraft design. I worked on roughly 36 different type satellites, various positions, various technologies, various products during my career there.
So then let's get an overview of Cesium Astro and what inspired you to found your own company.
I think if you look at the history of satellite telecommunication, shortly after Sputnik was launched by the Russians, although we had programs already ongoing, we proceeded with launching satellites, smaller satellites, telecommunication satellites. And these satellites have started to grow larger and larger because the rockets that we had available to us were from the Apollo era. Mm-hmm. And these rockets are large, and then if you're launching a satellite, you might as well utilize the mass to orbit and utilize the space in the payload fairing. And satellites naturally grew larger and larger. And the larger they became and the more power they had, you tend to have more investments in them. There's more capital investments involved, and you tend to make them more robust, make them redundant in all of the systems of the spacecraft on the satellite, and you ensure that they can last longer. So we went from traditional 8 years to 12 to 15 to 20, and some satellites last 25 to 30 years in the geostationary orbit. I'm specifically talking about the geostationary orbit, which is a valuable asset. It's a valuable real estate. You remain stationary so that you don't have to adjust your antenna on your roof, right? You're familiar with that.
Right.
Most people are. That's the origins of telecommunications satellites. When Arthur C. Clarke wrote a paper in 1945 and said if we place three objects 120 degrees apart at 22,350 miles above the equator, you can cover pretty much majority of the population of the Earth, and you can provide this relay network that really allows you to instantaneously provide an infrastructure, telecommunication infrastructure with satellites. That's the geostationary satellite that I'm talking about. So these satellites have started to grow larger and larger. And so getting back to your question, why did I want to invest in Cesium Astro and start the company? A couple of things I noticed was that as we were moving, these satellites, geostationary satellites, are really, really effective and really good for broadcast systems. When you have various sources of news and content and HBO and you name it, upload the signal to the satellite, and the satellite then broadcast it to the entire country, for example, like DirecTV and Dish Network and so on, anywhere in the world. For example, you have a beam that's shaped like the continental US, and then you broadcast it to the entire country. You got an antenna on your roof and everyone receives the same signal. But I started thinking about really we need point-to-point communication more and more. And of course, satellites adapted and have had spot beams and so on. But I really started thinking about that 2 points. One, I was thinking about that these satellites would be more effective as a system if they were smaller and more agile and they were refreshed in technology more often rather than 20 to 30 years. And the other thing was I thought that with the advent of internet and all of us wanting our data more agile and mobile to us, available to us, and nowadays we want it on our planes and we want it on everything. I felt that more agile payloads, when I say I meant myself and many others actually, that felt that we need to have more agile platforms where you can software define a beam that I talked about from the satellite. So you can change the coverage areas, you can serve areas where there's more demand better, and then areas that are less demand with a larger beam, and so on and so forth. Rather than these fixed beam technologies, software-defined phased array technologies provide you with this agile beams that can electronically steer, they can be shaped properly, you can automatically adjust the amount of power that's required. Power means throughput, speed in layman's term. And allows you to adjust the service based on demand rather than these fixed assets that are very expensive. They're already in orbit. They last 25 to 30 years. And what if your business plan changed? What if your business plan didn't work out? And so this agility and this smaller satellites was what got my attention. And I really wanted to become more familiar with this technology and pushed for this technology to get developed faster. That's one. On the defense side and military side, which I'm also deeply passionate about, I felt that these fixed beam technologies will also need to be replaced by more agile beams. It made no sense to me that, well, sure, you can have fixed beam technologies that illuminate parts of the world, but I felt that we need to use phased array technologies to provide better service, more agile service to the warfighter, to be able to make these systems jam-proof, spoof-proof, and ultimately deliver better service at a faster speed to the warfighters who defend our country. And so I felt also that our defense and military satellites need to be smaller, more agile, with software-defined payloads. And all of the above, what I just said, besides the performance improvements, also lowers the cost, in my opinion. Lowers the cost by several factors. I'm not saying that, and regardless of the orbit, you can be in low Earth orbit, medium Earth orbit, or GEO. I believe smaller satellites better serve the customer for most applications, not all. I still believe in GEO orbit. Some large satellites are still a very effective use of technology. But I felt many other ones that it's too detailed to get into this meeting, but better served with smaller satellites with agile payloads. Those are the origins of the Cesium Astro company. I wanted to bring this technology to market where you have software-defined, agile, multi-beam, multi-user satellites that are small, inexpensive, and can last 5 to 10 years in orbit, regardless of the orbit.
You know, you're talking about the history of satellite communications, and it brought to mind when I was early in my broadcasting career, and they installed the first satellite dish at the radio station where I worked to bring in the top of the hour news. And it was fascinating stuff, and it was this big, like 7-meter dish or something out in the back of the station. But it's just one of those things that came to mind. You addressed this next thing a little bit in the previous answer, but let's go a little bit more in depth into explaining a phased array to a layman like myself.
A phased array is a device that's been around. It's a technology that's been around for a long, long time. I think ultimately it was sort of conceived and conceptualized and invented well over 100 years ago. But ultimately, it was used in radar applications since 60, 70 years ago. It is a device that allows you to electronically steer these beams that I talked about. Let me explain what a beam is in a layman's term.
Sure.
A beam in telecommunication, kind of like your cell towers, what the cell towers are doing, the antennas that you have seen on these cell towers, these sort of rectangular white antennas that you see on cell towers, they're illuminating projecting a beam. You can think of it as a beam of light. It's not light, it's radio frequency. It's a different frequency than light, but it's essentially electromagnetic waves or photons, if you will, either one. This illuminating area, which is typically a circle or an oval shape, allows you to have a set of frequencies that your cell phones, for example, work from. And you drive through one beam, and then you drive through another beam, and then you drive through another beam. And the reason for this is that we can reuse the frequencies that are allotted to cellular infrastructure over and over again and provide more and more service. So as we've gone from first generation cellular technology to fifth generation 5G, we have made modifications, many, many modifications to better provide faster service to more and more people, okay? Sure. But for the longest time, these beams, whether they were on satellites, as I mentioned, or on cell towers, were fixed beam technologies. So these beams within which you can connect your radio, your cell phone can connect to a cell tower, or your radio station or your home can connect to a satellite, are fixed. They're looking at a fixed point and the beams are fixed. But as you go closer to Earth, for example, in satellite communication, the satellites are moving faster. They orbit the Earth every 90 minutes. And so you can't have a dish on your car, on your roof that you're constantly, or with a motor drive, you can, but the motor will wear out and you can't constantly track these satellites. So a better technology for that is a phased array where the antenna can remain stationary and fixed, but the beams electronically, without any moving parts, track the satellite, you see? So, and then the opposite way in cellular technology, as we go towards 5G and 6G, some of these phased array technologies are also being used where the beams can move and provide more dynamic, more agile service to areas where there's more demand. They can provide more power, shape the beam, and provide a more agile service to dynamically change the service pattern. So for example, the fixed beam technologies, if they're just pointing somewhere and there's just not as many people in that beam, you're sort of wasting that beam. Whereas if the other beam has a lot of people in it, you get congested. So what you want to do is you want to have these agile beams to dynamically steer. That's what phased arrays do. They just electronically steer the beams, but they provide many other applications. As I said, you can dynamically change the frequency per beam, which is important with, it's too detailed to get into the details of it. You can dynamically adjust the power to each beam, and you can, and in military applications, there's lots and lots of benefits with phased arrays that come from this multi-user, electronically steerable, dynamic, software-defined beams.
So then give us an overview of Cesium Astro's product families.
When I started the company, I wanted to be very disciplined, and it's a venture-backed company. And it is easy to say that, majority of the business is in the actual data, and I should just put up a satellite constellation and build satellites and put a constellation and sell the data. But that's not so easily done for a lot of entrepreneurs to raise $5 to $10 billion to an entire constellation. So what I felt I should do is to methodically move up the food chain as our company grows. And I still believe that there are three main reasons that you go to space. Besides lunar exploration and Mars exploration and other interplanetary missions that NASA does, and they're super, super important for a number of reasons. The main reasons you go to space for the Earth orbit is to provide three types of services. Earth observation, in a sense that you use optics to take pictures and so on. We're not in that business. The second reason is for telecommunication. We are in that business. And the third applications is called ISR, intelligence, surveillance, and reconnaissance. So our technology serves two of those three reasons that you go to space, regardless of the orbit. And everything that I mentioned, by the way, is regardless of the orbit. A lot of people get to know low Earth orbit now because of Starlink and coming of Amazon Kuiper and other things, but all orbits are important. All orbits still serve a purpose, and they serve each a particular purpose very, very well. And by the way, satellites are not the only method of communication. Satellites provide a good method of communication for certain applications, but you still need fiber optics or better for some things. You still need cable in some areas. You still need perhaps laser links are good in some applications. Laser links are good for inter-satellite links. Laser links are good for certain bulk transfer of data from satellite. But in general, satellite communications using radio frequency, electromagnetic waves, using phased arrays are becoming more and more popular, and ultimately will be in my opinion, will dominate the market. So in order to methodically grow the company, I thought it would be great if I built a phased array technology. This is really important because Cesium Astro didn't invent phased arrays. Phased arrays are available from some incredible companies in the US and around the world, like Raytheon and Northrop Grumman and Lockheed and Boeing and many others. But what I wanted to do was seeing what is happening with the advanced mobility that's coming to us. With eVTOLs, with autonomous vehicles, with our appetite for data in our cell phones, with in everything in our cars, on our plane. That you don't get good internet on a plane today. Right. What I feel what's coming to us is that there are many applications where phased arrays will be required, both for the 5G and 6G maturation of telecommunication. For several decades, telecommunication, in my opinion, was linearly growing, not like Moore's law in compute technology. But I felt that by mid 2000s, 2010s, there's going to be an exponential growth in an insatiable data appetite for data. And I thought that technologies like phased arrays will be required for everything. So I thought, if I can make a phased array, which is not just the antenna, it's an entire telecommunication stack. It has technologies behind the antenna that require for you to receive the signals, process the signals, and then transmit the signals. I thought, if I can build this technology that is not bespoke to every satellite, to every plane, to every platform, to every drone, and I can make it like an iPhone almost, where it comes out of the box and it just works. This is why we love our smartphones. It just comes out of the box, you answer a few questions, you push a couple of buttons, and it's yours, and it just works. Right. And I said, can I make a phased array that comes with hardware, software, everything you need, that a layman, that even companies, if you are Boom Supersonic, or if some other incredible company that's bringing about the next generation of air travel, they're focused on building the airplane. Their focus isn't on, being PhDs in RF and antenna. I said, can I build a phased array technology that anybody can buy from us as a product that comes out of the box? And it just works. It has the software, it has the graphical user interface. You can have a couple of engineers that are experts at it and then program it for their own use. If I sell it to our defense department, a military, again, they have some protected waveforms that they use. Can I build a product that is not bespoke to every platform? That's the way the state of the industry was, and it still is, in my opinion. The technologies are available, but if you buy them, there are these massive machinery things and products that you have to connect and you have to know. I wanted to build a product that just comes out of the box and works like an iPhone. And that was the technical origins of the company. And that's what we did. We built our Nightingale product you will see on our website. That was a single beam. It was sort of a proof of concept that a single beam product that can be sold as a product that we even have lowered the friction. You can even buy a box from us that allows you to hook up your laptop, hook it up to a wall plug, no RF instruments, no fancy instruments in your lab, and you can actually start programming it to your own benefit. Or you can use our software, but it's a complete phased array telecommunication system in a box. That was the novelty. That's where our trade secrets and some of our IP exists, because it's not so easy to build a phased array. I like to say phased arrays are the rocket science of electrical engineering. It takes every field of electrical engineering and mechanical engineering to build a phased array, from software, firmware, digital signal processing, power, RF, antenna technologies, and you name it. So that's what we set out to do. That was the first product. We introduced it to market 2-3 years ago, and now that's become a very popular product. We have customers in lunar missions, in drones, in all sorts of platforms, small satellites, large satellites. But the main product I was really after was a true multi-beam, very high bandwidth, phased array technology, complete, again, telecommunication system in essentially 3 boxes: a receive array, a processor, and a transmit array. And we just introduced that to market December of last year. And now it's just taken off for our company. Our company is just hitting its, so to speak, hockey stick. We have incredible number of customers who we deeply value, that both from commercial and military, that are coming to us. So that's the second product line, called Vireo. It's the name of a bird. And the third product line is, if you have the phased arrays for satellites and things, you might want to have them, you need to have them for the ground stations, for vehicles, for drones, for aircraft. The aircraft product actually was the motivation for our Skylark product. You don't get good internet in aircraft, but over the next 10 years, I believe all aircraft, all drones, all applications will have phased array technology, so that now you can dynamically track multiple LEO satellites, GEO satellites, MEO satellites, and dynamically change services. That's what our Skylark product does. It's an open platform where you can put anybody's waveform in it, the software that's required for connecting to a satellite in GEO or LEO or anybody else. Kind of like with your iPhone, you can or your smartphone, I should say, you can travel anywhere in the world, and it just works. You're going from AT&T service or Verizon service, somebody else's service, and it just works. And that was the idea behind our Skylark terminal, that it's a non-proprietary open platform. Anybody can, any airline, any aircraft manufacturer can install it. It has no moving parts. It can track multiple satellites, and you can change the software and work with any network. Again, that's one of the important features of Skylark from some other competing products. And it comes with everything you need to put it on an aircraft. And then fourth was what you just talked about, was the introduction of Element satellite. I can't stress this enough. We didn't build Element to be a satellite bus. A satellite's made up of 2 parts. A bus that keeps you in orbit. It keeps you healthy. It keeps the hardware nice and cozy and comfortable, because satellites go on one side are very, very cold, on one side are very hot, that faces the sun. So it has thermal features, it has solar arrays, it has batteries, it has computers, it has all the things required to keep you in orbit and nice and comfortable for the products to last. That's called a bus. And then you have a payload. The payload is the working part of the satellite. You can have optical payload, you can have a telecommunication payload, you can have all sorts of other payloads. So we, with our phased arrays, want to be the payload provider to the world, to the best technology out there, to the entire telecommunication and ISR customers. And we continue to sell that to many of our customers, both commercial and defense. But the reason for Element was that there are those customers, both in defense and commercial, who like our technology and want to buy an end mission. They're not system integrators. They can't just buy a phased array and then have to go shop around for a satellite bus. So we responded to a demand from our customers to say, can we buy the entire mission from you? And so 5 years ago, roughly 5 years ago, about January of 2020, I started hiring my first employee to sort of develop this bus that is very dedicated to our phased arrays, designed around our phased arrays. Phased arrays require, depending on frequency, require sort of a large Earth deck that faces the Earth. And then we wanted to design it so that it fits in a Falcon 9 on a ride share. And so it's a very specialized bus that we designed around our phased array. We worked on it for about 4.5 years, and we just introduced it to market. And as soon as we introduced it to market, now that all of a sudden has shown an incredible amount of demand for it. And so we're very happy about it. So what I call the first really software-defined, completely software-defined, multifunctional, small satellite bus is somewhere between 400 and 550, depending on the payload, kilograms, 400 to 550 kilograms, roughly. It can go up to 700 kilograms. A small satellite designed to last in low Earth orbit for up to 7 years at a reasonable altitude. And then we're planning to, over the next several years, to have versions of this for MEO and GEO as well, micro GEO, MEO as well.
My guest is Shey Sabripour, founder of Cesium Astro on the Xterra podcast. Take a moment right now to click subscribe to be sure you don't miss any of our podcasts, or if you're watching on YouTube, any of the videos from Xterra, the Journal of Space Commerce. So, Shey, what is the timeline for deployment and testing of the Element satellite?
Well, right now we have an internal goal. It's an internal satellite. It's our own investment. And our internal goal is to be on a Falcon 9 ride share on October of next year, 2025. Okay. It's entirely possible. We want to make sure we have a good satellite and very reliable, and it works for us and demonstrates. So it's entirely possible that if we need a few more months, we'll slip it to Q1 or Q2 of 2026. But my stretch goal for my team is to get it on a Falcon 9. But as long as it's perfectly reliable and we're happy, then that we have done all of our testing. So somewhere between October to sometimes in the middle of 26 is really the inaugural launch of our own Element satellite.
Yeah, timelines in the space business never slip, do they?
Yes, indeed.
Let's get a couple of more things here. First of all, earlier this year, you landed a NASA contract to develop lunar navigation technology. So what is that going to entail?
So that is part of the NASA. We got a contract from Marshall Space Center to develop this LunaNet communication and navigation technology. Obviously, there's no GPS around the moon, and so this technology, using what we call AFS technology, LunaNet calls AFS technology, allows you to have a navigation system that you can use around the moon, and that's the contract we're developing. As I said, AFS contracts is with Marshall Space Flight Center. We're developing right now a benchtop receive sort of radio, that software-defined radio that we have, and initially it can receive GPS signals, and it ultimately uses this AFS method of a navigation system, as I mentioned, the details of which are very technical, and we can talk about it at some other session.
Satellite communications infrastructures faces a lot of vulnerabilities, and we've all heard about some of the threats that have come from bad actors when it comes to our satellite communications. How does Cesium Astro help mitigate those, and what steps can the industry take to enhance its security?
I think security comes in multiple forms. One, obviously, is traditional technologies, not traditional, sorry, but advanced technologies in cybersecurity to be able to have the proper encryption such that satellites cannot be commanded by the bad actors or get access to the satellite internal information or or its operation in orbit, its attitude, its other attributes of a satellite. The other part of it is spoofing a satellite or jamming a satellite. And that's an area where phased arrays are really effective. This is one of the reasons that also why I wanted to build a complete phased array satellite. Phased arrays allow you to really provide some anti-jam technology that, again, the details of which are beyond the scope of this talk, but phased arrays provide. This is what I've just talked about, all the agile frequency assignment to any beam, channelization, sub-channelization of frequencies within a beam, processing within the beam, adjusting the power for each beam, and then this the subject of anti-jam, anti-spoof is just a few examples of I like to call tens, if not 100, features of phased array technology that are very, very important, and that's why I believe the future belongs to this kind of technology.
Just a couple of things more, and I want to talk about business just a little bit and find out from you what were some of your notable challenges in starting up a satellite company in what's a really competitive field, and what advice you might have for aspiring entrepreneurs in this new space sector.
Right. I think, as I mentioned, depending on how an entrepreneur feels that they have access to raising money or access to the venture capital market, I think having your feet on the ground, cash is king. Without money in the bank, you don't pay your people and there's no business. So the one lesson learned that I have, that I've exercised and I will always exercise, is enough runway so that if your product is delayed, if the customers you thought, sometimes an entrepreneur, me too, I thought that, gee, I built this very advanced product at an incredible price, incredible features, as I said. It just comes out of the box and works like an iPhone, and I'm just going to introduce it to the world to the world, and everybody's going to come to us. Well, guess what? It took a few years longer than I thought. You're a new company, and you have to establish yourself, and nobody's going to give you $100 million contract and trust their mission to a company of 10 or 12 people at the time. That's the lessons learned, that you have to really have your feet on the ground and say, okay, I'm just going to make sure that I'm very methodical and focused on getting the first box, the first technology, whether it's a aircraft or box or an electronic or anything. I feel that this methodical iteration of technology and introduction of one product at a time and growing up and moving up the food chain is really, really important. That worked well for us. I think the strategy of let's build the first product, let's sell it, let's make some money, let's generate some revenue, let's get the product in the hands of our customers. There are lots of programs in the U.S. from Small Business Innovative Research, SBIRs, that you can get from the government. Those are wonderful programs. Not only that's non-dilutive funds for an entrepreneur, but also it gets your product and gets your team in front of the real customers and give you feedback. And so you can improve your product. So I feel that the biggest advice I can give is being able to have your feet on the ground and not try to do too many. I mean, like if you have multiple billions of dollars, then you can develop a very large team and do everything at once, great. But for the rest of us mortals, if you really are trying to grow a company, having your feet on the ground, having 2 years of runway, 3 years of runway, I feel 2 years of runway is the bare minimum. It used to be when money was free and you could, raise a lot of money, that people say, I'm just going to have 6 months of runway and I'm good with it. I feel that having 2 years of runway, having your feet on the ground and methodically moving up the food chain, if you want to, is the right way to grow. That's my lessons learned, and I'm happy to share it. I think that's very important.
It's the classic definition of the 5-year overnight success.
That's right. That's very true. Yeah.
Just one thing more, Shey, and we ask this of all of our guests to close out the program, and that's to look down the road 10 to 15 years in space commerce and the role you feel like Cesium Astro is going to play, and tell me what you see. I
think telecommunication, as I said, is going through an incredible transformation. the advent of autonomous vehicles, which ultimately will happen. It may not happen in this decade. It may happen in the ultimate, full self-driving vehicles and full autonomous vehicle level 4, level 5 may happen in 2030s. Ultimately depends on advanced telecommunication. These cars are generating gigabytes, if not up to a terabyte of data every single day from every car through their camera or LiDAR system or both. They need to be connected to something to feed the neural net engine in various data centers and so on to make the autonomous vehicles work. That's just one example. With the advent of humanoid robots and advanced robots that you see, again, the processing that's required to teach these robots happens in these massive GPU farms. Now, it doesn't happen at the edge. Some processing happens at the edge. But the examples I like to use, Tom, is that you and I are having this conversation. You can change subject, you can ask me any question. We're having a good conversation. And our brains and body are consuming about 100 watts of power, 90, 100 watts of power. That's a light bulb, okay?
Sure.
And you and I can close our eyes and imagine a picture of our memory and so on, and we can process this, we can talk. We're having this low latency conversation with just 90 watts of power. That's incredible. And then you and I can have a sandwich, and then we're good for the next, hopefully several hours to 8 hours to have this conversation. I'm trying to show the efficiency of the human brain, the neural net of the human brain.
Sure.
It's really good at something. It's really good at that efficiency. But if you ask the humanoid robot to do the same thing that we're doing, it would consume a lot more than that, several orders of magnitude more than that. If you really asked it to learn the way we do, and if you really asked it to have this conversation. So my point is that the processing gets done somewhere else, and the edge processing allows the humanoid robot to function. And then,
right.
So that puts more stress on the Wi-Fi system, on the telecommunications system, and everything that's mobile. Add to it all the mobile devices, eVTOL taxis, all the aircraft and all the drones, and both in commercial and military. Everything that we want it to be connected, and we want it to be at high speed everywhere in the world. Now, many of us who live in a metropolitan area say, what's the problem? I get this question all the time. What's the problem? I have my iPhone and it just says excellent speed and I'm happy with it. Yes, but I live in Austin, Texas. You go outside of Austin for an hour and a half and you don't get such a good connectivity. So the majority of the world doesn't have good connectivity, even within the US continental. So I think telecommunication is going to go through this transition. I believe there will be a time where there's a network of various systems, satellites, fiber optics where it belongs, cellular network where it belongs, cable where it belongs, laser where it belongs, where everything is connected, and that you don't really care how your packet of information goes from one place to the other through what network. There's this machine network in my vision that decides what's the fastest way for this packet, what's the most resilient, what's the most a secure way for this packet of information to use the satellite, to use the LEO, to use the GEO. I mean, if you're on a plane and you want to download Netflix, you might want to use GEO because you don't care about the latency in that case. But if you're having a Zoom calls, you care. So there's a network, there's an intelligent network that will connect all of us and all of our machines and all of our cars that decides how to best utilize this natural resource, which is called the electromagnetic spectrum. What frequencies? Some frequencies go through walls and concrete, some frequencies don't. So you want to dynamically assign what frequencies, what technology, what path it should take. I believe that will happen over the next 10 to 20 years, where it's not this stovepiped, I own this, and I think it's going to be much more dynamic, and I think all of the technologies are going to work in harmony.
Shay, we are out of time, but I want to thank you so much for joining me on the program today. It's been an interesting and enlightening conversation, so thanks very much.
It is my pleasure, Tom. Thank you so much for having me.
Shey Sabripour is the founder of Cesium Astro. And that's going to do it for this edition of the Xterra podcast. Check out our YouTube channel and be sure to click on subscribe so you can stay up to date on developments in space commerce and be notified when we post new videos. You can get daily updates on space commerce by subscribing to the Journal of Space Commerce on Substack at www.xterrajsc.com. And one thing more, be sure to connect with us on LinkedIn and follow us on X at XterraJSC. Until next time, I'm Tom Patton. Thanks for joining us.